Hello and welcome to this video. I'm Ho Yi Hong from SMJK Kethua. Today, I'll be sharing with you 4 interesting science experiments to do at home. But before we get started, please remember, safety is always our #1 priority. Let's get started. To make elephant's toothpaste, we need hydrogen peroxide, dish soap, some food coloring, water, and yeast. First of all, add some hydrogen peroxide into the bottle. Next, add some dish soap. Shake it up. Add some food coloring. And make your yeast solution. Give it a stir. Now pour it into the bottle. And there you have it! Elephant's toothpaste! Cool, isn't it? Remember to clean up after the experiment. The foam is made as the dish soap traps tiny oxygen bubbles created by the chemical reaction that is happening inside the bottle. The thick foam oozes out of the top of the bottle and looks like toothpaste when it is being squeezed out of its tube. The activity is called elephant's toothpaste because the large stream of foam looks like toothpaste that is big enough for an elephant. Hydrogen peroxide is a molecule made out of hydrogen atoms and oxygen atoms. It can be expressed using the chemical formula H2O2. Under the right conditions, hydrogen peroxide will undergo a chemical reaction to break down into 2 parts, oxygen and water. We can write out this decomposition reaction as a chemical equation. Hydrogen peroxide will become oxygen and water. 2H2O2 will become H2O plus O2. When a chemical that is made up of only one molecule breaks down into two different smaller molecules, it's called a decomposition reaction. This particular decomposition reaction is also an exothermic reaction, meaning it gives off heat. If you feel the sides of the bottle, the plastic should feel quite warm. Yeast contains an enzyme called catalase. The enzyme is called catalase because it works as a catalyst in this reaction. A catalyst is a substance that speeds up the rate of a chemical reaction without changing its products. The yeast is added to the hydrogen peroxide to speed up the reaction. The catalase in the yeast speeds up the process of breaking down the hydrogen peroxide and thus produces oxygen and water more quickly. The oxygen gets trapped by the dish soap and forms the elephant toothpaste. We can write out this decomposition reaction as a chemical equation. Hydrogen peroxide will become water and oxygen. 2H2O2 will become H2O plus O2. Here I have with me a bucket of water. To create this gravity-defying water, get a good grip on the handle of your bucket. Slowly swing it. Once you're confident, go for a full circle. As you can see, the water is not coming out although the bucket is directly on top of my head. This is no trickery. There is water inside this bucket. I'll show you. When I flip the bucket over, the water spills out. This is because the force of gravity is acting on the water. But when the bucket is spinning in a vertical circle, gravity is still acting on the water. So why doesn't it flow out? When the water inside the bucket is moving, it has inertia. Inertia is a tendency of an object to stay in a uniform motion or in a straight line unless changed by an external force. So the water wants to continue to move in a straight line. The gravity force is also acting on the water. This is the same logic as a garden hose. The water coming out from the hose is called the arc of projectile movement. When the arc of projectile movement radius is larger than the radius of the spinning bucket, the water stays inside. I have a garden hose here to prove my theory. As you can see, the water flows out of the garden hose in an arc, which explains and proves my theory. Here's what you need to make your very own glider. First of all, some paper cups, a pair of scissors, some rubber bands, and some sticky tape. First of all, grab 2 cups and put the rest to the side. Take your sticky tape and tape these 2 cups together. You might face some difficulties here, so you can ask somebody else to help you. Once these cups are securely taped together, you're almost done. Put this to the side, grab some rubber bands, and tie them together. 4 or 5 should do. There we go. If you don't like rubber bands, you can use a stick and some rope. You just have to tie the rope securely to one end of the stick. Just like this. There you go. Your glider is now ready to take to the skies. Now, I am wrapping the rubber bands across the center of the glider. Just let go of the glider and watch it do its magic. I'm wrapping it with a string now. Whip it as hard as you can. Let me explain how the Magnus effect works. Essentially, when the cups spin quickly through the air, one side of the cup moves along the airflow, while the other one moves against it. This creates an equal amount of force that pushes the cups upwards based on Newton's third law, thus generating lift, allowing it to move upwards sharply. Because more spin equals more lift, when the cups start to glide downwards, they aren't spinning that fast anymore because of the drag that comes with all flying objects. But they don't fall to the ground immediately because they are still spinning. The Magnus effect still works on it and slows the descent of the cups. This Magnus effect is also quite important in the world of sports. Athletes that play tennis, table tennis, and baseball are using this every day but might not know it. I am sure that they are familiar with the terms topspin, backspin, and side spin, which determines how the ball curves mid-air. They can achieve this because of the Magnus effect. Have you ever been to a science museum and walked down a dark corridor? What you see is out of the norm. You're surrounded by streams of water illuminated by flashes of light. The water seems to be flowing back into the tap instead of out of it. You wonder to yourself, what on earth is going on? Actually, this effect is called the stroboscopic effect. Let me show you. Lights off. Here we go. First, a non-flashing light. As you can see, the blades of the fan move really fast. Next, a light flashing at 212 Hz. Well, you can see the blades appear to have been slowed down to a point where they look like they are not moving. Well, next up is 425 Hz. Finally, 500 Hz. Well, this one is just to show off another speed. You can barely make out the blades with this one. Let me explain what is going on. The light that flashes allows the eye to see the blades when they are lighted. If the fan blades appear to be not moving, means that the blades complete a number of rotations and always reach the same position when the light shines on them, making them look stationary. Similarly, the fan blades that move forward are because the blades complete multiple rotations plus a little bit more when the light shines on them, and vice versa if the blades move backwards. Well, that explains the streams of water flowing backwards. Remember, stuff you see isn't always the way you think it is. Science can play tricks on you if you don't think it through. I hope you guys enjoyed the video as much as I did making it. See you guys next time!